So in this part of the lecture, we'll discuss the majorization minimization algorithm in detail, and then the other parts of the lecture will discuss how to use a majorization minimization algorithm to derive the style algorithm for minimizing the L1 norm regularized least square loss function. So let's consider that we have a loss function which will denote by J of W, which is a combination of two different loss functions. So our first loss function is, let's suppose, A of y comma f w of phi of x over some data set. So in machine learning, typically, like, we have this y is a vector of target values, as we have been discussing in the supervised machine learning algorithm. This y is a vector of target values, and fw phi of x is a functional mapping from phi of x to the target values phi. And we have some data set of some m data points, and this error is a measure of the error that we will be incurring over this data set by a choice of this functional mapping fw of phi of xi, where this function f is parameterized by some learnable parameters w. And the second term in this loss function g of w is lambda times some r of w, where r of w is some regularization, is a loss function corresponding to regularization. So this can be L2 norm square of the parameters, or this can be L1 norm of the learnable parameters. So we'll consider a generalized loss function g of w, which will write it as the first term y comma f w phi of x over some data set d plus lambda times r of w, where lambda is a penalty. It's a model. It penalizes the model complexity, or it penalizes the learnable parameter w, where lambda is again a scalar between 0 and 1, or it can be more than 1 as well. I mean, we just took it between 0 and 1 because typically when we select lambda, we select its value between 0 and 1 typically in regulation, and that's why we mentioned that the lambda should belong to 0 and 1, but lambda can be any value greater than 1 as well. So we just erase this to avoid clutter, and we will write this loss function simply as g of w equal to the first term w of phi of x over some data set plus lambda times r of w. And in L1 norm regularized least square problem, the first term is actually the L2 norm of the error over the data set. So the first term is basically y minus phi times w squared, and the second term in the L1 norm regularized least square problem is simply the L1 norm of the vectors. So now let's suppose our goal is to minimize this generalized loss function, and let's suppose that for a particular choice of this function e and function r, this problem is, let's say, too complex to minimize directly, or in other words, this loss function is too complex or perhaps very difficult to minimize directly, right? So what majorization minimization does is that it replaces, as we discussed in the previous part of the lecture as well, it replaces the minimization of this loss function by a sequence of minimization problems that are easier to minimize. So MM, or the majorization minimization algorithm, will generate a sequence of vectors wk for k equal to 0 to infinity, such that limit k tends to infinity, wk is w star, where w star is equal to the argmin over w j of w. So this is what Majorization minimization algorithm in a nutshell does. It for the initial optimization problem, which has this loss function w, we replace this loss function by a sequence of loss functions that are easier to minimize, and then we iteratively minimize those or that sequence of loss functions. And by doing that, we generate a sequence of vectors. As in any iterative algorithm, for example, even in gradient descent, we generate a sequence of vectors at every iteration. Likewise, in Majorization minimization algorithm, which is an iterative algorithm, we generate a sequence of vectors wk, where in the limit k tending to infinity, wk approaches the optimal solution, w star, that minimizes the original loss function. Right. So, how's it relevant for our L1 norm regularized least square problem? So, in L1 norm regularized least square problem, we have J of W equal to A of y comma phi f of phi of x, which is simply the L2 norm squared y minus phi times W plus lambda times norm of W, L1 norm of W. So now we can see that 1, it is non-differentiable, and second, because of this L1 norm term, it's there's no closed form solution for minimizing this loss function J of W. So we will replace this non-differentiable loss function J of W by some function G of W, and by minimizing, so at every iteration of the Majorization minimization algorithm, we will select a function gk of W, where k is a kth iteration of the Majorization minimization algorithm. So to denote the dependence of this function g at every iteration k, we denote this function g as g subscript k of W, which means that at every iteration k, at kth iteration, we'll select a function gk of W, and by minimizing the sequence of these loss functions gk of W, where k goes from 0 to infinity, we'll eventually be able to minimize the original loss function. And to be able to do this, this function g of k has to satisfy some properties. So how do we derive this function g of k? So we'll now discuss the Majorization minimization algorithm first. We'll discuss what are the constraints on this function g of W, and then we will write the pseudocode of the Majorization minimization algorithm, which will lay the foundation for deriving the style algorithm. So let's assume that at kth iteration, we have some guess of the parameter W. We have some wk which is perhaps generated by solving some optimization problem. It can be our random guess or any initialization of the parameters W. So we just let's assume we just randomly initialize the parameters W at kth iteration as wk, or let's suppose we obtain this W by minimizing optimization problem. Then the next goal would be to take this wk, and the value of the loss function would be j of wk, corresponding to the value of W equal to wk. So now the goal would be to compute wk plus 1 such that j of w k plus 1 is less than j of w k. So we can do this by ensuring that g of k satisfies two properties, right? So this is our goal. Given the initial guess wk, our goal is to generate wk plus 1 such that the loss function has lower value at w equal to wk plus 1 as compared to the value it had at w equal to wk. So this is what majorization minimization algorithm does. So the first step of the majorization minimization algorithm is to majorize j of w. That is, select a function g of k of w such that gk of w is greater than or equal to j of w for all w belonging to the domain of function j. So this is the first step of the majorization minimization algorithm. So the g of k, so we majorize j, the original loss function g of w, which means that we find a function g of k that is an upper bound for the original loss function j of w. What upper bound means is that this new function g of k will have higher or equal value just like j of w for all w belonging to the domain of the function j. The second condition is that g of k should be equal to j of w for w equal to wk. So the second condition is that so we can say that the first step is to ensure that we select a function, or these can be assumed as conditions on or the constraints on the function g of k. So the function g of k should satisfy that it upper bounds the original loss function j of w, and the second constraint that this loss function should satisfy is that gk of wk is equal to j of wk. So once we select a function g of k that satisfies these two properties, that it upper bounds the original loss function j of w, and second is that it has the same value as function as loss function j at w equal to wk. So once we do this, then we can minimize, we can compute wk plus 1 as arg min over w gk of w, where the subscript k denotes that this function is selected at the kth iteration. So this function g is not a constant function. It will change at every iteration of the majorization minimization algorithm. So now the question is, what this function g, what is this function g that we should select? So apart from these two conditions, apart from g satisfying these two constraints, g should have also the following properties. Property number 1, or you can say it should have only one property, is that g of k should be a function that we can easily minimize. And second, at least for the L1 norm regularized least square problem, we should select the function g of k that is perhaps differentiable. as well as convex at the same time. Because the original loss function is convex, therefore it would make much more sense if the function g of k is also a convex function. So at least for L1 norm regularized least square problem, we'll have two conditions for selecting a good function g. Is that one, it is easy to minimize, and second, it is differentiable as well as convex. So now we will see a graphical example as to how the majorization minimization algorithm works, and then we will derive the pseudocode for the majorization minimization algorithm.